Now let's get to grips with the Big Bang, the origin of our universe, in a hot, dense state over 13 billion years ago. What's the evidence for the Big Bang? There are four major pieces. We've already talked about the expansion of the universe measured through galaxies. It's a cosmic expansion of space-time, not a Doppler shift. And if we run the film of our universe backward, run the movie backward, the galaxies would all be closer together, so we would project to a time long ago when all the galaxies were on top of each other and the universe was smaller and denser. That's pointing to the Big Bang. The most definitive evidence that we'll talk about in detail is the cosmic microwave background radiation, a signal of radiation that is the same in every direction in the sky and so smooth to 1 part in 100,000. And it's almost perfectly thermal, which is to say representing a single temperature, and that temperature is just under 3 degrees Kelvin. We also find that deuterium and helium were synthesized in the early universe because the universe itself was once the temperature of the core of a star that can make helium by fusion. And in fact, it made most of the helium in the universe. And also, through deep surveys with the Hubble Space Telescope and ground-based telescopes, we can see directly that galaxies evolve. We can watch the evolution of the universe by looking out in space, back in redshift, and we find galaxies that are younger, smaller, more irregular. They look like they are evolving in time. And they again point to a time when the universe was hotter and denser. The status of the Big Bang model is important to recognize because it's an audacious idea that we can explain the entire universe and everything in it, an event that happened so long ago. So we hold it to the standards of the scientific method, as we would all good ideas. A good scientific model should make predictions that can be verified, and the Big Bang, since it was first proposed in the 1940s and 50s, has made 2 predictions that were verified 20 years later. There was the discovery and characteristics of the microwave background radiation and the expected helium abundance in the universe. The model predictions agree with almost all current observations. There are a few flies in the ointment from recent research, but the model is very sturdy. And there's also a lot of indirect evidence that the universe was hotter and denser in the past. We can look at the evidence of helium abundance from the early universe, and we can calculate, using computers, it used to be done with equations, what the physical conditions in the universe were in the first few minutes. And when you do this, you can calculate that in the universe, the expanding situation of just after the Big Bang, with a temperature of hundreds of billions of degrees, deuterium could have been made, lithium, and helium. And the proportions of those elements just happens to perfectly match what we see out in space. Here's a graph where the vertical axis is the abundance of these light elements measured in various cosmic locations, in stars or intergalactic medium. And along the horizontal axis is the density of normal matter as a fraction of the matter that would close the universe. And we see the vertical gray bar is a band of ordinary matter density that accommodates all 3 light elements measured abundance. That's extraordinary agreement because these elements are created and destroyed in many different ways. For the single parameter model of the Big Bang to explain them is a very great success of the model and gave people a lot of confidence that it was correct. But the definitive evidence for the Big Bang is indeed the microwave background. We know the universe was hotter and denser in the past, but the microwave background and the helium abundance cannot really be explained in any other way. It's important. If you want to have a rival to the Big Bang, the bar is actually very high because you have to explain all the evidence that the Big Bang explains and then make predictions that can be confirmed. And that's partly why the Big Bang has now stood the test of time for pretty much 50 years. The Big Bang will say that there are hundreds of thousands of Big Bang photons in every breath around you. The Big Bang is all around us because it was the entire universe that was filled with this primordial radiation. The Big Bang is just a theory, but a theory with a web of evidence to support it. The theory, however, and the model are mute about the cause of the Big Bang. So that's important to recognize, that the Big Bang is only a physical description of the universe from an early, incredibly hot, dense state. Does not formally tell us what caused the Big Bang, nor what preceded it, if anything. So let's look a little closer at the microwave background radiation. The universe is immersed in a sea of radiation that was discovered serendipitously in 1964. And in the physics, 380,000 years after the Big Bang, the universe, expanding, had cooled enough for free electrons to become bound into hydrogen and helium atoms, stable atoms, neutral atoms. Without the electrons to scatter them, photons were able to travel unhindered through the universe. This is like the curtain raising, both literally and metaphorically, of the universe, because it became transparent. And so the radiation we see with radio telescopes is directly an image of the universe 380,000 years after the Big Bang. Looking back in time that far, we're looking at a universe where the overall temperature was about 3,000 Kelvin, similar to the photosphere or atmosphere of a cool red dwarf star. So if you could have been around the universe at this incredibly early time and strange state, it would have been like being in a dense red glowing fog. Since this time, that radiation has traveled through expanding space for billions of years, and the universe has expanded by a factor of 1,000, reducing the temperature by that same factor from 3,000 to 3 Kelvin, just a little bit above absolute zero. So when we look at the microwave background, we can make an analogy with a cloud, and it's not too bad. Very different physical situation, of course, but we're looking at the surface of the glowing fog that filled the early universe. Just as when you look up at a cloud, you're seeing the surface of the cloud is not a physical layer, it's not a hard thing, it's a smooth boundary to a region where the density is high enough that light doesn't travel freely. And so inside a cloud, it's opaque because photons bounce around off water molecules and don't travel freely. The edge of the cloud counts the distance where light travels directly to your eye, and you see the edge of the cloud as a boundary. The microwave background radiation is an analogous boundary in the early universe to the time between when atoms became neutral and light could travel freely, and before that when everything was ionized and very hot and light could not travel freely. The microwave background, typically called the CMB, is the highest redshift of anything we can see. And the universe was not only 1,000 times smaller and hotter, but density goes as the cube of size, so it was 1 billion times denser than it is now. A very strange physical situation. Here's how the observations of the microwave background have improved since its discovery. The top map you see is of the whole sky from Penzias and Wilson, who were given the Nobel Prize some years later for this discovery, made with this horn-shaped antenna in Holmdel, New Jersey. These two men were engineers working for Bell Labs, doing research on early telecommunications satellites, and they were using that horn antenna to test telecommunications satellites, when instead of looking at a satellite signal, they found a strange hiss, radio hiss, that was the same frequency almost everywhere in space. The band in the middle of the maps you see is the Milky Way itself, so we're talking about away from the Milky Way. This was the 3-degree Kelvin radiation that came from the Big Bang, perfectly matching a prediction that had been made 20 years earlier by George Gamow. In 1992, the COBE satellite was launched, and you can see the improvement in its map of the sky. COBE was able to detect the first fluctuations in this radiation at a level of 1 part in 100,000 that represent the seeds for galaxy formation. That work also received a Nobel Prize. And then in 2003, the WMAP satellite, the Wilkinson Microwave Anisotropy Probe of NASA, produced the exquisite map you see in the lower right. So our observations of the microwave background have improved 1,000-fold since the first microwave observations, and it's exquisitely accurate knowledge about the early universe. Also, it's worth noticing that this is not just for radio astronomers. If you tune a TV, an old-fashioned one, say with a tube rather than a liquid crystal display, if you can find such an old TV, I'm sure there's one in your garage or your aunt or uncle or grandfather's garage, tune it between stations and you'll see speckle patterns, interference. 1% of the specks of any TV tuned between stations are actual interactions of the phosphor with microwaves from the background radiation of the Big Bang. And I actually suggest that as a recreational activity. There's a lot of TV stations, a lot of channels, but sometimes there's just nothing on. So if you want a more zen-like, relaxing experience, sit in front of your TV, tune between stations, get a nice drink, and watch the microwave background. Watch the Big Bang. It's sometimes the best thing on. The observations with the microwave background were able to show an important aspect of the universe. We've seen that in general relativity, space can have various geometries because mass energy curves space-time. And so a logical question is, does the universe have a global curvature? And we saw the examples of the global curvature. That curvature could be positive, like the surface of a sphere, or negative, like the surface of a saddle. This diagram and this animation shows that as radiation travels through the universe, it will be bent according to the curvature of space, if space has a curvature. But if space has no curvature and is flat, it will not change the size of the speckles across that span of time. What we actually observed was the middle diagram here. And so observations of the microwave background compared to an expanding universe model say definitively that space is flat to within 1%. There's no global curvature of space-time. And that's an important thing to recognize about the universe we live in. We also have to consider in cosmology the idea of horizons. And there are different forms of horizons. The one we're familiar with on the Earth is the Earth's curved surface creates a horizon, so we can't see beyond a certain distance on the Earth's surface. We've encountered recently in this course the black hole event horizon, which is an information barrier that we can't see into because photons or particles cannot escape. The universe has a horizon that's called a cosmological horizon, and that's essentially the boundary to our vision in the universe, not because there's an edge in space itself, but because there's a distance beyond which photons haven't had time to reach us in the age of the universe, 13.8 billion years since the Big Bang, and that forms a limit to our information. The behavior of light in the universe as it's expanding is bizarre. Light travels simply and directly in the universe. The upper little animation shows that light traveling within the solar system behaves completely normally, 300,000 kilometers per second. We can say how long it will take to go to a place and to come back. But the early expansion of the universe was actually faster than light speed. In other words, any 2 points in space were moving away from each other faster than light speed. And what that means is that light traveling between those two regions back then would have receded and would have not reached its destination. As the universe decelerated, because of the influence of dark matter over cosmic time, that changed to the point where galaxies stopped moving away from each other faster than light speed, and that would allow the light to gradually reach a distant galaxy from its source. The cartoon animation below tries to convey this. As the galaxies separate, they're moving so fast that the light wave is not catching the other galaxy. But eventually they slow down and the light wave reaches the other galaxy. And that's why the edge of the observable universe is 46 billion light years away. You might think naively that it should be about 14 billion light years away, because that's how old the universe is. But because the universe was expanding faster than light speed, the edge or horizon of our universe is about 3 times the naive expectation, 46 billion light years. The implication of this is quite profound. It means that the physical universe, all there is, all space-time and all matter and energy, is bigger than the observable universe. In fact, this is not a bug, it's a feature of the Big Bang. It's a natural consequence of the Big Bang model that because the expansion was so rapid early on, there are absolutely and must be regions of space we haven't yet observed and haven't yet seen. Now, if we wait long enough, they'll come into view because the universe decelerated to the point where that light will eventually reach us. But we have to understand that the physical universe is much larger than the observable universe, and the factor by which it's larger is rather uncertain. It might be 10 or 100 or even 1,000 times bigger. And those unobservable regions are likely to just be like our parts of the universe. They'll have stars and galaxies and people too, we think. Another feature of the Big Bang model that was the only major modification to it in the year 1980, from the hands of Alan Guth primarily, working at MIT, is the idea of inflation. The Big Bang has trouble explaining 2 features of the universe, although it's generally very successful. The universe is very smooth, that's the microwave background radiation with uniform temperature to 1 part in 100,000 that I talked about, and it's also flat, also measured from the microwaves. The flatness and smoothness of the universe is a little hard to explain, And it means that scientists came up with an idea of extremely rapid inflation, where the universe expanded exponentially early on, seen in the era in the blue vertical bar on this timeline. Just 10 to the minus 35 seconds after the Big Bang, incredibly early epoch that it's almost an unimaginably small interval of time. The mechanism for inflation is still unclear, but it's probably associated with the grand unification theories that are under discussion in physics and hope to be tested that seek to unify all the forces of nature except gravity. So the universe began from a tiny, tiny size, inflated to a size that's macroscopic, about the size of a beach ball, say, and then started expanding at a more steady rate, the Hubble expansion, as we're familiar with. And that's now our standard model of the universe. The implication of this is quite profound. It means that inflation probably stretched quantum fluctuations into the large-scale ripples that became the seeds for galaxies. In other words, quantum fluctuations were literally the seeds for galaxies that would eventually form by gravity when the universe had cooled enough. It's an extraordinary proposal, and it has some evidence to support it. Inflation makes the universe flat and smooth by design, because regardless of the curvature of space-time early on, the incredible expansion by many orders of magnitude would have flattened out space. Imagine a balloon that's small and curved, and if you inflate it to an enormous size, any small patch of it will seem to be flat. Look at the diagram on the lower right. So you get flatness and smoothness by design, so that's not really a confirmation of the idea. It implies that vast regions of space are beyond view, because that early expansion was so dramatic. And this idea does have tentative support from microwave background observations using satellites. And here's how that is done. It requires extremely difficult observations of the polarization of the microwave background photons. So the idea here is that in the early universe, at the time of inflation, there were gravitational waves caused by the roiling space-time of that moment, and that the exponential expansion would have imprinted those gravitational wave signatures on the microwave background radiation. When you work through the math, it means the way you could detect the imprint of gravitational waves from inflation onto the microwave background is through observations of the polarization, or preferred orientation of an electric or magnetic field, of the microwaves. Now, this has been observed recently with telescopes from the South Pole, and there was a false alarm detection that got front page headlines in 2018, but actually had to be retracted. They were confused by a contaminating signal from dust in the Milky Way. But everyone is looking for this, and new satellites and telescopes are currently doing this test. If this test succeeds, it will be strong affirmation that the era of inflation actually happened. This idea that the universe is bounded in time but not space is fundamental to cosmology. It's important to recognize that superluminal expansion, faster than light motion of one point in space from another, does not violate any law of physics. It's special relativity, which we've already encountered, that declares that the speed of light is an absolute limit. The expansion of the universe is governed by general relativity, and general relativity sets no speed limit to the rate of expansion. It's nowhere in the equations. The universe can expand as fast as it wants. So as time goes by, ever more distant regions come into view, and we see no limit in space itself. If we look back to a redshift of 1.3, a point at which light has been stretched by a little more than 100%, the object we see, and there are many galaxies that we see this far away, was moving away from us at the speed of light at the time that light was emitted. Since then, the universe decelerated, and that light has reached us after 4 or 5 billion years. But at a redshift of 1,000, where the microwave background radiation starts, 2 points were moving apart at 60 times the velocity of light. So extraordinarily rapid expansion back at that time. So the consequences of the standard Big Bang model are that the physical universe is much larger than the observable universe, and we're subject to a horizon, an edge to our vision, bounded by time. The consequence of the inflationary Big Bang idea, which has a lot of support, is that a microscopic region, a quantum-sized region of space-time, became our visible universe, and that the universe is a quantum entity. And it's an extraordinary inference from physical theory about our entire universe. And that's the end of this topic.